All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good. Sounds good. Hang in there. All right. Things are going to get busy soon. So we do have a midterm exam coming up in about 2 weeks. And I'm hoping we can finish up all the classical stuff today. Just so that we keep that nice cutoff before the. All right, so one announcement that I posted homework 3 this afternoon. The homework 3 is all about constraint optimization. So half the homework assignment will be on equality constraints. The second half of the assignment will be on inequality constraints, which is what we're gonna go over today. And so the due date for that assignment is gonna be Monday, October 7th. So you have a little bit over a week, maybe about 10 days to do this assignment. Okay. All right, so at this point, you should be able to do, from this minute, you should be able to do about half the assignment. I'm hoping by the end of the day, we'll finish all the inequality constraint stuff and, you'll be able to do the rest. Okay, any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. All right, so actually the first thing I want to do today is I want to go back up to this figure up here. Because we're moving on to the realm of inequality constraints, right? So we know that whenever we do an optimization problem, ultimately we're optimizing or we're minimizing the objective function. But oftentimes we'll come across problems where we need to constrain the design variable in some way. So we spend a lot of time talking about equality constraints, where equality constraints are simply just equations with equal signs that constrain our design variables. But oftentimes we'll also come across situations with inequality constraints as well. Okay. And that's kind of what we're covering. Okay, so the difficulty with inequality constraints is that they're not as restrictive as the equality constraints. And so it's oftentimes it's the case where you can have a bunch of inequality constraints, but they don't actually simplify your problem at all. In fact, they kind of make it a bit more difficult. Okay, and so just to kind of give you a visual example, right? So typically in a two-dimensional optimization with one equality constraint, the equality constraint basically defines that our solution or our optimum has to sit on some kind of line that goes through the domain. Okay. And so, knowing that our solution has to be on that line, we've effectively restricted our problem from a two-dimensional problem to a one-dimensional problem. And, that actually brings a lot of benefits to us. Okay. Okay. On the other hand, for inequality constraints, they instead define a region where the optimal solution can exist. Okay. So while it is restricting, instead of being available to the entire, domain of the design space, it's not restricting enough for us to actually make a difference in how we find it. Okay. So there's kind of a challenge with it, and ultimately, when we're solving these types of problems with inequality constraints, we have to use kind of a guess and check approach in order to define the optimal solution. Okay. Okay, so I just wanted to kind of review that and mostly just kind of show these two figures, right? And so with equality constraints, we're restricting our design space pretty thoroughly, where inequality constraints, we're not as restrictive. Okay. Okay. So let's talk about before we introduce kind of the main theorem that goes with inequality constraints, which are the Kuhn-Tucker conditions. Let's kind of briefly discuss what it means for a constraint to be binding. So a constraint is considered binding when the optimal solution sits right on the boundary of that constraint. literally the constraint is binding the optimal solution. Okay. So all equality constraints, so every constraint that's defined by an equal sign inherently are binding because equality constraints require that your solution is bound to that equality constraint. So if you think of the figure above, right? So our equality constraint for that example for we have a diagonal line going through a domain. If that constraint is equality, then our optimal solution has to sit on that line. Right? So, but just by its very nature, equality constraints are binding. Okay? Inequality constraints, on the other hand, don't have to be binding. As long as the optimal point sits within the valid region, then it's considered valid. But it could be far away from the boundary. Let me kind of show you what I mean by that. Let me go ahead and draw the same figure as before. We have a two-dimensional optimization. We have x1 on the horizontal axis, x2 on the vertical axis. Let me go ahead and draw the valid region like this. Okay. So let's say that all points below this line are valid. Okay. So as long as our optimum design point is within that orange region, then we're good. Okay. Let's consider three different points here. Let's consider P1 be within the valid region. So the value for x1 and x2 for the point P1, that puts it in the valid region. Let's consider P2. P2 is going to sit right on that line right there. Okay. And then P3 will define Okay, so let's characterize both of these points, right? So we can either characterize these points as a free point or a bound point. A binding. Okay. We can also characterize these points as either valid or invalid. Okay, so let's start with P1. So P1 we can see it is very squarely in the valid region. So right away we can already say that P1 is valid. And another reason we can say that's valid, or another way to say that, is that it satisfies the inequality constraint. Right, so that answers kind of the second question there. As for the question of whether it's free or binding, we characterize P1 here as free because even though it's in the valid region, it's not on the edge, it's not on the boundary of the inequality constraint. But in other words, we call P1 a free and valid point. Okay, now let's look at P2. So P2 is sitting right on the edge of the valid region there. So, you know, being on the edge still makes it valid. Okay, so we can say that it's valid. But since it's right on the edge of that region, we can say that it's bound, or the constraint is binding that point. Okay. And then finally P3, right? We can probably guess what P3 is going to be. So since P3 exists outside of the valid region, we can first of all say that's invalid. And it's not sitting on the boundary at all. And so we say that it's free, but invalid. Okay, so that's just kind of a visual example of kind of what it means to be a bound point or constraint to be binding. Okay. Now, of course, you know, the most interesting point here that I want to focus on is P2. And so P2, you know, we can see from this description here that P2 is a valid point, and so it satisfies the equality constraint, the inequality constraint, excuse me. But it does so in a very particular manner, right? So not only does it satisfy the inequality constraint, right? Remember, all inequality constraints are given by the form of something like this. We have G of x1, x2 is less than or equal to 0, right? Remember, that's our standard form for the inequality constraint. If we have a point that's bound, like P2, you know, P2 will satisfy this inequality constraint, but it does so in the equality form, right? And so it's almost as if this constraint is an equality constraint when that constraint is binding. And so in other words, you know, we could have solved this problem if P2 was the optimal point. You know, if P2 was the optimal point, then we could solve this problem as if and treat this inequality constraint as an equality constraint. And that's really nice because, you know, if we can treat certain inequality constraints as equality constraints, then, you know, we can treat it as such. And, you know, we've already gone over a lot of methods to solve problems with equality constraints, right? We have our direct substitution method and we have our Lagrange multiplier method. And in truth, you know, those aren't the only two methods that are out there too. There's also other methods that, you know, we're not covering in this class, but, you know, we know how to deal with equality constraints really well. And so if we can kind of reform our inequality constraints as, you know, equality constraints, then then we're kind of in business. So then that's kind of what helps us solve these problems. Now the question becomes, how do we know, how do we know ahead of time if an inequality constraint is going to be binding or not? Sometimes it's obvious, right? So sometimes you look at a problem and it's kind of very easy to tell which of the inequality constraints will be binding. But a lot of times it's not. A lot of times you're going to look at a problem and you're not really going to know, if the problem is binding or not. Okay, let me pause here for a second. Are there any questions on this so far? Okay, cool. Okay, so we actually have a tool that we've already gone over that can help us with this. Okay, and that is the Lagrange multipliers. And so if you recall, when we solve problems with Lagrange multipliers, the value of the Lagrange multiplier itself told us about the nature of the constraint. Okay. Remember the way we solve problems with Lagrange multipliers, we assign one Lagrange multiplier per constraint in our optimization problem, right? And later on, if we found that the Lagrange multiplier was 0, then that constraint had no effect on the optimal solution at all. And so if we kind of take that notion into consideration, and we think about kind of our definitions of free and bound points, right? If you look at some of the free points in our product here, right? So let's say P1 and P3, right? Those ones are not really affected by the constraints. You can kind of make that argument, right? And so if P1 was, for instance, if P1 was the optimal point and P1 was automatically in the valid region, then we might as well have not considered the inequality constraint at all, because it didn't even have an effect, right? And so you could make the argument that if your inequality constraint is not binding, then that inequality constraint actually plays no impact on the optimal solution at all. And so if we solve the optimization problem, so just to kind of give you an example, right? So let's say that we solve an optimization problem we treat it as if it were an unconstrained problem, so we don't, you know, factor in any of the constraints, and we get our optimal solution, right? If that optimal solution automatically satisfies the inequality constraints, then, you know, there was really no reason for us to include those inequality constraints to begin with, right? And so another way to kind of put this mathematically is that if an inequality constraint is not binding, then its corresponding Lagrange multiplier should be 0. And if it's Lagrange multiplier 0, that means we can ignore it in the optimization. And so this idea, right, this idea of kind of using the Lagrange multipliers to kind of, you know, sort different constraints as either binding or non-binding, that's kind of central to what's called the Kuhn-Tucker conditions. And so, you know, let me preface this by saying that, you know, the Kuhn-Tucker conditions, there's a lot of variations on it. In fact, you know, there's other people who tack their names onto this because people have taken the Kuhn-Tucker conditions and kind of, you know, modified it for certain situations. And so if you look this up, you'll probably get like a very long Wikipedia article with, you know, lots of different things and very complicated math. We're gonna just kind of use this in kind of it's kind of a simplest, kind of purest form. Okay. So the idea with the Kuhn-Tucker conditions, at least from a practical optimization standpoint, is that if an inequality constraint is not binding, then, you know, we shouldn't have to include it in our optimization problem at all. And the way that we can exclude a constraint from the optimization mathematically is we set its Lagrange multiplier to 0. Okay. So let me give you the Kuhn-Tucker conditions themselves. Okay. So we'll write out its mathematical form, and then we're going to jump right into an example to kind of see how to actually use them. So the Kuhn-Tucker conditions. What they state is that a constrained minimum point it must satisfy these the following mathematical relationships. Okay. So in these equations, you know, I'm going to use kind of the typical nomenclature that we've used up to this point. So f is going to be our objective function, it's going to be our design variables, and g's are going to be all of our constraints. Okay. Okay. So the first one is partial f, partial xi. So this is all the partial derivatives of our objective function. And so if we have multiple design variables, we're going to have multiple equations. Okay. plus the summation j is equal to 1 to m of lambda j partial g j partial xi. This has to equal 0. Okay. For I goes from 1 to n. I here represents the number of design variables. And then the j factor there, which goes from 1 up to m. This represents the numbers of constraints. Okay, so this equation here looks kind of complicated, but this is nothing more than just our first condition, right? So remember, when we're solving for the optimal point in a multivariable optimization, we take the first derivative of the objective function plus all of the Lagrange multiplier terms as well. Okay, we take the first derivative, we set it equal to 0, and then we use that to solve our system. Okay, so this equation right here is nothing more than just our usual first derivative condition. Okay. And so the other condition that we have is that if we take this the summation, or excuse me, we take the multiplication. We take the multiplication of the Lagrange multiplier multiplied by the constraints for each of our constraints. Okay, that has to equal to 0. Product of the Lagrange multiplier corresponding constraint and this has to be true for every single constraint. The product of those two has to equal 0. Okay. And so this can happen one or two ways. And so we can either have the Lagrange multiplier be 0, or the G constraint can be 0 as well. Okay. Remember, when we put our constraint, we've always put 0 on one side of the equal sign, right? And so if the constraint is equal to 0, then our constraint is binding. Okay. But if our constraint is not binding, then the lambda is set to equal to 0. Either the constraint is binding, or the Gj is equal to 0, okay, or the point is free and we set the Lagrange multiplier equal to 0. So that's kind of the two ways that quantity can equal 0. Right? Either the constraint is satisfied in the equality form, okay, or we manually set the Lagrange multiplier equal to 0, one way or the other. Okay, but just because a point is free doesn't mean that it's valid, right? So we saw that in our illustration earlier. It is possible to have a free point that's technically invalid. And so just because you have a free point doesn't mean that you can just disregard it, right? You still need to satisfy the condition. Okay. And so one of the other conditions of the one of the other conditions for the Kuntagler condition is that for a free point, they should still satisfy the or they should still be in the valid region. Find something new where, I write out, so the conditions here are all kind of, it's multi expressions here. And so the contacting conditions are all of these mathematical statements in one. I'm trying to add notes here to kind of give them some context and to kind of explain what each step is, but it's getting a bit long. So unfortunately, I won't be able to display all 4 statements in one, but hopefully the notes are kind of helpful. Because sometimes you see theories like this, you see mathematical equations, and without the explanation, without the context, it's a little bit dry. So I'm hoping to add a bit of context. Okay. Especially in terms of how we're going to use it. Okay, and so the last contactor condition states that all of the Lagrange multipliers have to be positive. They either have to be positive or 0. Now, this last condition there, that last condition is going to change if you have a maximization problem, right? So the contactor conditions is one of those optimization theories which kind of inherently assumes that you're doing a minimization, okay? If you're doing a maximization problem, then the sign for this one kind of flips. Zoom out, try to get it. Okay. So these 4 statements combined, are the contactor conditions for a constrained optimal. Okay. Remember, so that first mathematical expression there, that's the one that we've been using all this time. So that's just our usual first derivative condition. Okay. Probably the most important statements here that we're going to use are 2 and 3, which states that the product of the Lagrange multiplier and the constraint is always going to equal 0. Okay. And that's either going to happen if the Lagrange multiplier is set to 0 or the constraint is satisfied in the equality sense. Okay. Number 3 is that if you have a free point, it should still satisfy the inequality constraints. Okay. And the last point, we're not really going to use that all that much because we're not going to do too much with the Lagrange. But I included it here just for the sake of complete. Okay. All right, so these are the contactor conditions, right? And so of course, to use these conditions, you have to kind of know, or you have to have some intuition in terms of, which of your inequality constraints are going to be binding right from the get-go. Because the way we're actually going to use this is that, we're going to be given an optimization problem, and you have to kind of decide, which constraints are going to be binding and which ones are not. So the ones that are non-binding, you're going to go ahead and just remove those from the optimization. We're just not going to worry about it. But the ones that are binding, we include that in our Lagrange function, just like we've use this. Sometimes it'll be obvious, like I mentioned before, we'll do kind of a very quick, just because I think it illustrates this concept very neatly. I'm going to give you a preview of one of the homework assignments in homework 3. We're not going to solve it completely, but just to kind of give you a preview of it. But sometimes, sometimes it's not very clear which ones are not, and so When it's not clear, you kind of have to just do a guess and check. And so you kind of have to guess and guess, which sets of constraints are going to be binding. Then you would solve the problem, okay? Then after you solve that problem, you go back and check and see if all your constraints are satisfied. If it is, that's great. You can move on. If not, then you have to try a different combination. Okay. Any questions on the contractor conditions before we jump into some examples? Okay. All right. So the first example that we're going to do, I'm not going to solve it all the way because it's one of your homework problems, but I think it does a really nice job of kind of illustrating this idea of this, which constraints are going to be binding or not. Okay. So for this example, let's pretend that you're stuck inside of a room. For some reason, you went into a room, someone locked the door, and can't get out. Okay. So let me draw a schematic of the room. So just like any good building design, let's assume that you're sitting in a room that's defined by a Cartesian coordinate system. Okay. So one of the corners of the room is going to be at the origin. Let's be 0.00. And then just to just to make it a little bit different from your homework problem, let's say that the room has a triangular shape. Okay. And so the walls of the room, one of the walls of the room are going to be the vertical axis here. Another wall axis. And then the other wall is going to be given by that there. So let me go ahead and define the vertices of the room. Let's say that this is point 0,4. And this is 0.4,0. Okay, so it's a right triangular room. And then here's you inside the room. And you're sad because you're stuck in the room. Okay. So you need to get out of the room, but there's no way for you to open or break out of the room from the inside. Okay. But from one of the gaps in the room, let's say that there's small peepholes in the room, right? You see someone off into the distance, right? So let's say that you see someone over here. And then let's say that this person has the position, let's say that they're located at point 6, comma, their exact kind of Cartesian. All right. So to get out of the room, you have to get help from this person. That's the only person you've seen in hours, right? But the room, unfortunately, is very insulated. So your voice doesn't carry outside. So the only way for you to get this person's attention is to get as close as you can to his location while still within the room. And so what we want is, our design variables in this case, or what we're going to solve for, are the optimal values for X, your X position, and your optimal values for your Y position that will position you as close to this person as possible. Okay. All right, any questions on the setup for the problem? Your phone is dead, by the way. You can't call for help. You have to yell it. Okay. All right. So, we're not going to get too much into the weeds here, right? But the main thing I want to highlight here is the constraints for this problem, right? So the constraints for this problem is that you have to be within the room, right? So you can't leave the room. So that kind of defines our valid region. Our valid region is inside the room. So to kind of constrain our optimization, we can use the walls of the room as inequality constraints. So for instance, we know that our room, the origin is at 0, 0, right? And we have one vertical wall going up, right? So our x position has to be to the right of that wall, right? So our first inequality constraint is that x must be greater than or equal to 0, okay? And we can do the same thing for the y coordinate as well. So the y coordinate, we have to be greater than or equal to 0. Right, so that'll put us in kind of the positive coordinate of there. Our third wall is that slanted line, right? And so if you look at the coordinates of where it intersects, we can see that if we use kind of the very basic kind of y is equal to mx plus b, we can see that the y-intercept for this wall is at 4. And then we can see that when x is equal to 4, then our y value here is 0. Okay. So the equation for that wall is y is equal to minus x plus 4. And so that sets our third constraint. The third constraint is that y must be less than or equal to minus x plus 4. So that's wall 1, wall 2, wall. Okay. So these three inequality constraints must be satisfied in order for your position to be within the room. Okay. Okay. So this is one of those situations where you can kind of look at the problem and you can kind of try to guess intuitively which of these constraints will be binding. Okay. So if the person that's going to help you is located at position 6, 11, right? You're probably going to be as close as you can to this slanted wall. I don't know exactly where you would be, but probably be somewhere right here. You want to get as close as you can to that slanted wall because it doesn't make sense for you to be on the left wall, right? Because the person isn't, it doesn't have the person helping you doesn't have a negative x value, right? It also doesn't make sense for you to be on the bottom wall either, right? Because the person doesn't have a negative y value. And so kind of just based on intuition, you can kind of already tell that the one constraint here that's going to be binding is going to be constraint number 3. And so from here, you can kind of solve the problem with that assumption, right? And so if you make the assumption that's your binding constraint, you can solve your optimization. What you're probably going to find is that when you do solve the problem, your other two constraints are automatically going to be satisfied. So that's the idea with the Kuhn-Tucker condition. So for the Kuhn-Tucker conditions, we're going to look at a problem, we're going to assume some of the constraints are binding, okay? We're going to solve our problem, and then we're going to hope that all your other constraints are going to be satisfied. Okay. All right, any questions on this example here? Okay, so that's a preview of one of your homework assignments. And so, from here, of course, you would have to formulate the objective function and then optimize it and so on and so forth. But, hopefully this kind of gives you a little bit of a head start. All right, so let's do another example. And this other example will work all the way through. Let's do another example where it's not really clear which of the constraints are going to be binding. Okay. So for this problem, this problem is just going to be a simple kind of math problem. So there's no kind of story that goes along with it. So let's say that we're given the following objective function. Say f of x and y is equal to x times y. Very simple objective function here. All right. What we want to do is we want to maximize this function here, subject to the following two inequality constraints. The first constraint that we're going to have is that x plus y has to be less than or equal to 50. The other constraint is that 2x plus y has to be less than or equal to. Okay. So we have two inequality constraints in one objective function, and this is a maximization. Okay. So this is a pretty standard. Kind of inequality constraint problem. Okay. Two constraints. We don't know which one of these are binding, and so we're just going to have to try to guess and see. Okay. So kind of the annoying thing for solving these types of problems, if you don't know which of the constraints are binding, is that you may end up having to solve the same problem many times over with different combinations of constraints. Okay. Unfortunately, that's just kind of how the method works. And once we kind of move on to nonlinear programming, these problems will become easier. But, because we're kind of stuck with the classical methods, we're kind of stuck with this guess and check. Okay. Let's try one. So this is attempt number one. So for attempt one, let's assume that neither of the constraints are binding, and we just solve kind of the pure unconstrained problem. All right, and so if neither constraint is binding, we have just very simply f of x and y is equal to x times y. Let's take our derivatives. Take partial f, partial x. Okay. Our first derivatives in this case are pretty simple. So we take the partial derivative of f with respect to x, we just end up with y. We're going to set that equal to 0, just like we normally do. Okay. You can also take the partial derivative of f with respect to y. Okay. And so if we do that, we take the partial derivative with respect to y, we get x. And that's also equal to 0. So in this case, we do get a solution here. Okay. And so our solution is just x and y is equal to 0. And so at this point, after you solve for an optimal point, the next thing you have to check is you have to check whether this point here satisfies the constraints. In particular, you're going to check all of the non-binding constraints. So all of the constraints that you kind of assume that to neglect with this attempt, you're going to check to make sure that it satisfies those ones. Okay, so our constraints, our first one is x plus y has to be less than or equal to 50. Okay. We're going to plug in our optimal value for x and y. So x and y optimal values here are 0. Okay. You have 0 plus 0. 0 plus 0 is just 0. And 0 is indeed less than 50. And so this constraint is satisfied. Now let's check our other constraints. Our other constraint is 2x plus y less than or equal to 60. Once again, we're going to plug in our optimal values here. So we have 2 times 0 plus 0. Of course, that's going to be equal to 0. And 0 is indeed less than 60. So this is also okay. Right, so that seemed kind of too easy, right? And so we had these inequality constraints, and we kind of just said, we don't care. We're just going to solve the problem unconstrained. And turns out our optimal solution does actually satisfy those constraints. Right? But wait a minute, if you remember from the original problem here, our goal was to maximize this objective function. Okay, so the last thing that we're going to check here is we need to make sure that this point 0, 0 is indeed a maximum of this objective function. And so luckily for us, this is we basically treated this as an unconstrained optimization. So we can basically just compute our typical Hessian. Let's compute all the second order derivatives. So we have partial squared f squared. Partial squared f, partial x squared is just going to be 0. So because the first derivative of f with respect to x was y, and so we take another derivative with respect to x. Y does not depend on x, and so we just get 0 case. Same thing for the second order derivative with respect to y. And so remember the first order derivative of f with respect to y gave us x. And so if we take another derivative with respect to y, that's going to give us 0. And then lastly, we need the cross derivative. So partial squared f partial x partial y. In this case, we take the derivative one of each, and then we end up with a 1. And so if we look at our Hessian matrix, looks like the following: 0, 1, 1. And so in order for this point, in order for the point 0, 0 to be a maxima, then the Hessian matrix evaluated at that point must be negative definite. But we can see something right away, right? Kind of a red flag for us here. If we look at the top left entry of our Hessian matrix, we see we have a 0. Okay. And to remember, the top left entry of the Hessian matrix is significant because that is our first principal submatrix. Right? The fact that this is 0 the fact that it's 0, right? The fact that it's 0 means that it's not a positive number, nor is it a negative number. Okay. This means that our point here is neither a max nor a min. Okay. Which makes sense, right? And so we have an objective function. There's no negatives in the objective function. It's just x times y. It doesn't make sense for the maximum point to be 0, 0, right? That's just that just kind of wouldn't make any math. So this kind of confirms it. And so even though the point 0, 0, the derivative is indeed 0 there, but it does satisfy all the constraints, it's not a true maximum. Okay. It just happens to be kind of a saddle point that's within our fallow domain. All right, so we have to continue. So we have to basically continue and assume one or the other of the constraints are fine. All right, any questions on this so far? Okay, all right, so let's continue. So let's try another constraint. It's going to be try. By the way, even though try 1, we ended up with not a valid solution. It's usually not a bad idea to try that, right? So try when you have a problem with all inequality constraints, try the situation where none of the constraints are binding, and you may end up with an optimal solution. Right? But it's not a bad thing to try. Okay, so for try 2. Let's assume that the first constraint is binding, but the second constraint is non-binding. And so our first constraint was x plus y has to be less than or equal to 50. Okay. So if our first constraint is binding, then we have to include it in our optimization. Okay. And so we're going to form a Lagrange function that incorporates that first constraint. So we're going to incorporate the constraint into the objective function. And we're going to do it using Lagrange multipliers. Okay. Let's go ahead and form our Lagrange function. So our Lagrange function for this case, x and y. We're introducing another design variable, which is the Lagrange multiplier for that constraint. Right, so remember the way we form our Lagrange function is that we include our original objective function. So the original objective function in this case is x times y. Okay. And then to that, we're going to add another term that incorporates that constraint. Oh, by the way, let's before we do that, let's put our constraint in standard form. Before we include any constraint into our objective function, it has to be in standard form. So our constraint in this case is x plus y. Since we're going to assume that this constraint is binding, I'm just going to turn that less than or equal to the sign into an equal. So our constraint is in this case is x plus y has to equal 50. Remember, to be in standard form, 0 has to be on one side of the equal sign. So I'm going to take that 50 and subtract it from both sides. We have x plus y minus 50. So that's the constraint that we have in standard form. And that's what we're going to plug into our Lagrange. Okay. All right, so we have x, L of x and y and lambda 1 is equal to xy plus lambda 1 multiplied by our constraint here in standard form, which is x plus y minus 50. Okay. So we're still assuming the second constraint is equal to 0, or it's non-binding, excuse me. So we're not going to include it here. Okay. So now that we have this, new Lagrange function here, let's go ahead and solve it. And let's see. First of all, what optimum that we get, and whether that optimum satisfies our constraints. Okay. So first, let's take partial L, partial x. Okay. So the derivative of our Lagrange function with respect to x. Okay. We do that, we get y plus. We take the derivative of the constraint there. A lot of those terms are going to be equal to 0 because they don't depend on x. And so all we're left with is lambda 1. We're going to set that equal to 0. Next, we're going to take partial L, partial y. Once again, we're going to get x plus lambda 1 is equal to 0. Okay, so pretty short here. Okay, and then for our new design variable, which is the Lagrange multiplier, let's take its derivative. Okay, so we have partial L, partial lambda 1. And so for this, we just end up with our plus y minus 50. That's equal to 0. Okay. All right, so we have a new set of equations here. Okay. So just like we normally do, we're going to solve the system of equations for x and y. So one thing that kind of jumps out to me in this system of equations is that both the first equation and the second equation have a plus lambda. Okay. So let's subtract these two equations. And what that's going to do is that's going to eliminate lambda from the equation. Okay. Y plus lambda 1 minus x plus lambda 1 equal to 0. Okay. We're subtracting the right-hand sides too, but the right-hand side is just 0 minus 0. Okay, so if we do this, we can see that both the lambda 1s here are going to cancel out because we have a positive lambda 1 minus minus lambda 1. I do too many negatives there. So those are going to cancel out. And then all we're left with is y minus x equal to 0, which we can solve for here. And so, if this constraint is binding, then y and x have to have the same value. Okay. So let's plug that into our third equation, because our third equation is only a function of x and y, okay? So if y is equal to x, let me plug in for y. And so we plug in for y, we know that y is equal to x, we have x plus x is 50, 0. I'm going to move that 50 to the other side of the equation. The x plus x are going to combine and become 2x. And so we can solve this equation for x, and what we get is x is equal to 25. And then based on our relationship earlier that said that y has to equal x, we also get y is equal to 25. So that is our optimal solution in the case if the first constraint is blank. All right, any questions on how we solve that system here? Okay, cool. All right, so we have this optimal result. This makes a lot more sense, right? And so it's not 0, 0. So we have 25, 25. That's going to give us a much higher value than before. Okay. But before we stop here, let's check to make sure that this actually satisfies all the constraints, right? We know that this satisfies the first constraint already because we assumed that it was binding. So since we assumed that that constraint was binding, we don't need to check it again. I mean, you can if you like that satisfaction, but you don't have to. Okay, but we do need to check other constraints. So the other constraint that we assumed was free, we need to check to make sure that one is actually satisfied. And so the non-binding constraint, or the one that we ignored in this case, was 2x plus y has to be less than or equal to 60. Okay. We're going to plug in our optimal values for x and y, and we're going to pray that this satisfies this constraint. Okay. Because if it satisfies this constraint, then we're done. We're Gucci. All right, so let's plug in our values here. So we have 2 times x. So 2 times x is 25. And then y here is also 25. Okay. We perform the arithmetic. We have 2 times 25 is 50, plus 25 is 75. So obviously that is not true. Okay, because 75 is not less than or equal to 60. And so unfortunately, this was not the right combination. So we need to kind of keep going and assume, now we're going to assume that the other constraint is this. All right. This is kind of how the conceptor worked, right? So we've solved this problem twice already, and we don't have the right solution just yet, right? So we just need to keep going. So in theory, there's 2 more combinations that we can try, and so we can try the second constraint being binding, or we can try both constraints being binding. Well, let's hope that we get it on the next one. All right. So let's try. We'll do try number 3. And so in try 3, we're going to assume that the other constraint is binding. 2x plus y, so less than or equal to 60. Is binding. Okay. So let's put this in standard form. Standard form, we have 2x plus y minus 60 is equal to 0. Okay. I just move the 60 over to the other side and I change the less than or equal sign to equals. Okay. And then now let's write our Lagrange function with this new constraint. Okay, so our Lagrange function. I'm speeding up a little bit just because I want to finish this example. Spoilers, this is going to be the right one. All right, so we're not going to do a try for. So our Lagrange function in this case is our original objective function x times y plus lambda 2 multiplied by our. Okay, so let's take our partial derivatives here. Partial L partial x here is going to give us y plus 2 lambda. That's equal to 0. Now let's take the partial derivative with respect to y. So we take the partial derivative with respect to y, we get x plus lambda 2 is equal to 0. And then we're going to take the partial derivative with respect to lambda 2. This just gives us our constraint, 2x y minus 60. Okay. So once again, we have a system of 3 equations and 3 unknowns, but the most important unknowns here are x and y. Okay. So let's solve the first 2 equations and eliminate lambda. And so to do that, I'm going to multiply equation 2 by 2 and then subtract the 2 just to eliminate that lambda 2 there. Okay, so we have y plus 2 lambda 2 minus 2 times x plus lambda 2, 0. Okay. The lambda 2 terms are going to cancel out. And so what we're left with is y minus 2x equal to 0. In other words, y is equal to 2x. Okay, so let's plug that result. So now that we have y is equal to 2x, let's plug that into our constraint. So we get 2x plus 2x, 60. This gives us 4x is equal to 60, or in other words, x is equal to 15. And so we plug in that result of x is equal to 15 back into our y equation. Okay, so we know that y has to be equal to 2x. So we get that y is equal to 30 in this case. Okay. All right, so very quickly, right before we finish up, let's check to make sure that this satisfies our first constraint. For non-binding constraint states that x plus y has to be less than or equal to 50. Okay. And so we plug in our optimal values for x and y. X is 15 in this case, y is 30. So we have 15 plus 30. This has to be less than or equal to 50. We add those 2 together, we get 45, which is indeed less than 50. All right, and so from here we can stop the problem. And so we have an optimal solution. It satisfies all the constraints. Okay, we had to assume that the second constraint was binding. Now, of course, at this point, you can, you should verify that this is a maxima. And so, you would go through and compute the Hessian and whatnot, okay? But unfortunately, we're out of time, but I will leave you guys to do that on your own. Okay? And so when we come back on Tuesday, I have one more example for this inequality constraints, okay? That one's a little bit more of a practical example, and then we'll do that, and then we'll kind of wrap up this section on classical optimization. Okay. Any final questions before we wrap it up for today? Okay, all right, so that's all we got time for today. So thank you guys for coming out. Hope you guys have a good rest of your day. Hope you guys have a good weekend, and I will see you guys next week. Midterm, yes. So midterm is going to be on October 10th. So I believe that's Thursday. It's going to be the same week that homework 3 is due. So homework 3 is due Monday of that week, and then midterm will be Thursday of that week. So yeah, homework 3 is October 7th, and then midterm's October 10th.
Hey, Professor, I have a quick question.
Sure. What's up?
Um, when you went to eliminate lambda 2, why did you multiply? Well, I see why you did, but how did you multiply 2 times that second equation?
Yeah, so so since the right hand side of that second equation is equal to 0, we can
Mhm.
set this entire equation by 2.
Oh, okay. So you just the entire thing. Okay.
Yeah, yeah. So I'm really kind of taking advantage of the fact that we have 0 on one side of it.
Okay. Yeah, that answers it. All right. Thanks, Professor. Have a good one.
Have a good day.